there are multiple search trees that we can construct given the same set of elements. And because of that, it effectively matters in the way that we look at how to search for these elements within the tree. Now, let us first introduce the concept of a map. Okay, so this is a topic that is going to cover this week as well as next week. Today, we're going to talk about a specific type of map that is called a sorted map. Okay, so next week, we're going to talk about unsorted maps. But the concept of a map is just key value pair. So if you've been using hash map, hash table, and things like that, that's basically a map. So the key value pair is that you specify a key and a value. So the key is like an index, and then the value is the content of what you actually want to store, right? So for example, let's say if it's in the class and we want to maintain a grade book, so then that grade book, the specific grades are going to be the values, but then we need a key to identify the grade book of a specific student. Now the key could be either your name, for example, or your campus ID, something that identifies you uniquely so that we can retrieve that in an efficient way, and it identifies you in an unambiguous way. So the basic operation of a map basically is get and put, right? So when you put something to the map, it means that you create a new mapping. So you have a key value pair. Okay, I'm going to put a new student as well as a grade book, so that it is like I'm putting a new value. Now get is like fetching. So I just specify a key, and then you're going to return me the value that is associated with that. Now remove is similar to a get, except that in the case of a remove, we also remove it. So it means we will return the value, but we will make sure that it doesn't exist anymore within the map. And then we have some iterable collections. One is a key set, just return the set of keys. Values, so in this case, we just return only the values. Or the entry set, in which case we're going to return the key value pairs. So that we have all these things in place. Now, this is an example of the set of operations of what you want to do on a map. So for instance, if you put 5A, the 5 here is a key, the A is the value. Well, it doesn't have to be just a single value. It could be like an object. It could be another data collection. So in that case, then you're basically creating a mapping within a map. So then you store that mapping. 5 is going to refer to A. So you put 7B, so then the map is going to grow, then it's going to take on more values there. 2C, so it's going to take on more. 8D, right? Now, when you say put 2E, but previously 2 already is associated with C, so then we're just going to overwrite, right? So C is overwritten to E, right? And then the gets will basically fetch things out, but it doesn't remove anything. If you try to get something that doesn't exist, it just returns a null. And when you try to remove, then it's going to basically take out and delete stuff from the map, right? And in that case, then you are removing the stuff. Okay, so now that's basically the content of the map and the operations that we can do on them. Now, as far as we are satisfied with direct keys, which means that all we care about is exact equality of the key, then the regular kind of map, like a hash map, would probably suffice, right? We don't need anything more than that. Now, in some cases, we would like to make use of a sorted map because it induces a certain ordering of the elements that we can define range queries. So range queries, it means that we are not looking for a specific value, but we're going to determine a range of values, in which case we want to fetch everything that meets that particular range. So for instance, let's say if you are looking for flights, right? Most of the time, you're not looking for a flight at a specific time, but you have a certain period of time in which you're going to tolerate this. So in that case, let's say we specify that we want to find flights between 9:30 and 8 o'clock on a certain date, right? From a certain origin to a certain destination. Now, this is a range search because if you want to use actual map to do this, then you have to iterate over the possible keys to see which keys are actually within that range. So instead of doing that, we are going to maintain the ordering of the keys within the data structure itself so that we can easily identify the elements that meet this requirement. So which means that there is going to be a certain way that we can define ordering, right? So for example, we can ask for what is going to be the first element within this map, what is going to be the last one. Can you give me ceiling? Ceiling means that I don't know the exact key, But if I give you a particular key, I'm going to find, I want you to find the next closest one to that, right? The floor is the same, and then you have the submap, which is kind of a range. So I'm going to specify the from and the to. So just like the flight example earlier, so then tell me from this key to this key, get me all the elements there. So let's say if we take a look at an example, okay, so we're going to use a binary search tree to implement all these features of all these methods that the sorted map wants to do. And we just want to identify a specific implementation feature here, which is that we're going to assume that the binary search tree will always be a proper tree. Proper means that it either has 0 or 2 children, right? So in that case, the way we're going to do it is that every node that is at the leaf, we're going to give it 2 null children, and we're going to call that external nodes. Okay, we're going to call that external nodes. So every one of them, so think of it like your sentinels, the way that we define sentinels in your linked list. So they are like dummy nodes that that make the processing a little bit easier, and therefore we maintain them. So we're going to maintain this convention for this implementation. So basically every leaf node would have 2 external nodes, both of which are null. So they are like children, right? They're the children of these 2 nodes, but they are the 2 null pointers. Okay, so now once we do that, then we can make a distinction between what we call the internal nodes. These are the ones with actual keys. So the one with the numbers, integers, and so on, the keys, right? These are internal nodes. And all the null pointers are going to be external nodes. Right, so these are going to be the null, right? But we are going to treat them as if they are real nodes, so that we can talk about them in the same way that we talk about any other nodes in the tree. Now, let's say if we do it in that way, then we can have an implementation that is called tree map. It's a form of a map that makes use of binary search tree. Now, so the simplest case is a get, and we're going to implement a get in terms of a search. So we're going to search for that particular key. If we find it, the search is going to terminate at some point. It can terminate in 2 possible ways. So one is that it's going to terminate at the internal node, which means some node with a key, which means that we have found it, right? The second way that it can terminate is that it can terminate at an external node, which means that we don't find the key. So if we don't, so we terminate at an external node, so we return null. Otherwise, then we return the actual value itself. But the basic point here is that this is implemented on top of the binary search tree. So basically, we're going to make use of the binary search operations like a search. So in that case, then the search is going to help us to get a get, right? Now to put, then it's going to be like inserting into the binary search tree. So just find the exact location through a search, and then you insert it there. So let's say we want to get the following examples, right? These are examples of using those features of sorted map on the tree map. So first entry is going to get us the smallest value. And if we start from the root, we know how to get the smallest value. Just go all the way to the left. So left of left of left of left, and at some point, you're going to terminate. And at that point of time, you will know that you have ended up at the smallest value. Last entry is the largest value, so we know how to do that. We just go to the right? We keep going to the right until we get the largest one. Ceiling entry, it means that we are looking for a specific key, but we are not completely sure that we get this exact value. But what we are saying is that find me 65, and you can't find me 65, then find me the next largest value. So now 65 there happens to be there, so then we found it, right? So no problem, then we return 65. But if you are trying to find 70, 70 doesn't exist. But we're going to return the next largest value, so which is 76. But it was still returning only one value, just the next largest one. The floor is the opposite. So either you get me that key or get me the next smallest one that actually exists. So in that case, it's the same. If I'm finding 65, I'm going to get it. But if I'm finding the floor entry of 70, which doesn't exist here, so I need to return 65, which is the in-order predecessor of 70. Now, the lower entry and higher entry are similar to the floor and the ceiling, except that we don't accept equality. So it means that if I'm finding 65, even though it's there, I still want a lower value. Okay, so in that case, I'm still going to return 54. So the higher entry is going to return 76. Now, finally, we have the submap. The submap is a range search. So we specify the range from 65 to 93. So the first value is inclusive. The second value is exclusive. So we're not going to get that, right? So which means that what we are interested in then is going to be exactly this particular subtree, right? Oh, so we need to go up there again because the 88 is included. Okay, so now this is going to be what we're interested in. Now, in that case, we get a range of values, which means that we're going to get all the nodes that we have here. Now, all these operations, right, if you look at, well, not exactly pseudocode, but some kind of hint of how to get that, right, all of them will depend on first searching for the node. So, and searching for the node, because before you can delete, you can insert, you can search for anything. I mean, you can even define a range, you have to search first. So now searching operation within a binary search tree. And the issue with that is that then it's going to determine basically the key complexity of the binary search tree itself, which means that as long as my searching is bounded to a certain complexity, everything else that I do will also have that complexity. In this particular case, that complexity is h, right? H here being the height of the tree. So for me to get, put, remove, first entry, last entry, whatever it is that I need to do, I always have to go through the height of the tree. Now, this height then is of interest. How high can a binary search tree be? Now, as we have seen, even in the tutorials and so on, it can be as high as the number of elements. Now, which means that in the worst case, any kind of searches, I will have to do OM, right? Now, of course, this is the worst case. We are not expecting. We are going to get more or less a random insertion of the nodes, and therefore our tree is more or less short, and then we get something like a log n complexity. But that remains a hope, right? But in the worst case, we might really end up with this particular situation. One of the key idea behind improving the efficiency of all sorts of range search mapping, right? So that you want to implement using a binary search tree concept, you need to be able to bound the height of the tree. Now, if you can bound the height of the tree, in fact, if we were to give a definition to this, and we say that a binary tree is balanced, if for every internal position, so the internal positions are the ones with the keys, right? The height of its children will differ by at most 1. So it means that if I take this, for example, right, and it has 2 children, the left and the right. So what I want to make sure is that the height difference between them is at most 1. So they could be the same. It could be the left is taller by 1, or it could be that the left is shorter by 1. So in all these cases, we still consider them balanced. Now, if we guarantee that particular property, then we are going to get the following guarantee, that if we can make sure that the tree meets the concept of being balanced, then it will be searching within O log n time. Okay, and later on we're going to see justification as to why that is the case. All right. Now, so our objective is to create a balanced tree, right? And to create a balanced tree, we need to be willing to make some adjustment to the structure of the tree. And then here, we're going to come back to what we discussed earlier in the tutorial question 5. So you can have multiple shapes to the binary search tree. But as long as they contain the same set of elements, they are basically still the same container, because they are going to still return you elements in the same in-order search, right? Means if you have in another sequence of the same set of elements within the binary search tree, then it doesn't matter what the shape is. You would always get the same sequence of elements out. Now, so let's say, so we're going to look at an example, right? So what we need to do in the context of this is to be willing to make changes to the shape of the tree. And the basic change that we're making, we're going to call that a rotation. So we're going to call that a rotation. And okay, so we're going to take a look at this concept of rotation. What does it actually do? Now, let's take a look at this one first, right? Let's assume that y is the child of some node z. Okay, so we don't see it here, but it is some other node z, right? Now, in this case, if y is the left child of z, if y is on the left of z, then we know that everything within this subtree is going to be smaller than z. And we can rearrange everything on this left subtree, and it is not going to affect our relationship with z. So which means that we can isolate this problem and say that, okay, I'm going to ignore what the ancestor is doing, right? I'm just going to focus on this subtree, and it's not going to affect whatever is happening on top, as long as I keep this still as a binary search tree. So if I keep preserving that property of a binary search tree, then whatever is happening on top, below here, it's not going to affect my ancestors. Now, if this were to be the right child of z, right, which means that the whole y and all its descendants are going to be the subchild, the subtree of z on the right, then they're all going to be larger than z. So I can rearrange them in any which way, and it doesn't matter because they will still be the same subtree. Okay, so that's why we are going to look at this being part of this subtree. Okay. Now the next thing is to look into the concept of, let's take a look at this subtree, and we are going to do an in-order traversal. So we're going to do an in-order traversal on this tree on the left. So the in-order is going to be, so T1 here is some subtree. So it's going to be T1, X, T2, Y, T3, all right? So we're going to have this particular in-order traversal. Now, whether the shape is like this or the shape is like this, the in-order traversal is the same. So even if you do it here, it's going to be T1, X, T2, Y, T3. So which means that given the two nodes X and Y and its subtrees, we have two different ways to rearrange them in such a way that still give us essentially the same in-order traversal. And that is what we want to preserve, right? So which means that this particular operation is called rotation. So it's called rotation because in this case, X used to be the child of Y, but now here, X is now the parent of Y. So we are rotating the tree by changing who now is the root of the subtree without changing the basic sequence of the nodes within the subtree. So which means that the rotation changes the shape of the tree without changing the essence of what are the elements that are being contained within the subtree. Now, if this rotation can take place, so it turns out that in most cases, we can actually enlarge the scenario a little bit more, and we can reduce it to 4 cases of basically what we call restructuring. Now, in the case of restructuring, we're going to involve not just 2 nodes, X and Y, we're going to involve 3 nodes, X, Y, and Z, and their subtrees. Now, so let's take a look at this one, right? So now in this case, so if I were to do an in-order traversal on this one, so I'm going to have T1, so A, then I'm going to have T2, and then B, and then I'm going to have T3, and then C, and then I'm going to have T4, right? So I'm going to have that particular sequence. Now, whether is any of these 3, A or B here, or even if we go here, I can still do the same thing, right? So if I do in-order traversal here, so I get T1, A, T2, B, T3, C, and then T4, right? So all these different shapes are giving me the same in order traversal, which means that as far as binary search tree is concerned, I can consider them equivalent. Equivalent in the sense that they give me the same ordering of elements. Now, it turns out, though, that within this sequence, the one that we desire the most is the one on the right here, because they are more balanced. So because if you see here, what happens with A here is that supposing that T1, T2, T3, T4, let's say they're all of the same height, so then the Z here is going to have a lopsided thing, right? Because the T1 here is going to be some height, H, for example. If T4 is also height H, by the time we come here is H plus 1, this is H plus 2, which means that I have a specific instance where I have a subtree is rooted at A, right? With two children, Y and T1. Well, in this case, one has a height of H, the other one has a height H plus 2. So that is a difference of more than 1. So which means that this is not balanced, right? So whereas the balanced configuration is given on the right here, right? This is the balanced configuration. So which means that given all these different possible configurations of these subtrees, we would like to all go to the particular shape on the right, where we have B being the middle one, and the rest are going to be oriented around B in a balanced way. Okay, so now the way that we are going to do this is the following. So let's say that you want to do a restructuring. If you call a restructuring on a particular node, so what it means is that you're going to take a node X, for example. You're going to take the pattern of X, which you call Y. You're going to take the pattern of Y, which is you call Z, right? So we're going to restructure on the X. So X has a pattern Y, Y has a pattern Z. So then we're going to restructure between these three. And what we're going to do is that between X, Y, and Z, we are going to label them from the left to the right to be A, B, C. So if Z happens to be the root on the left, right? So then A, B, C. In this case, X is the leftmost, so A, B, C, right? Now in this case, you still have A, B, C, right? A, B, C. Now, so once we have that particular label, then we are going to make B the root of the subtree, the A and the C to be the left and the right children, and T1 and T2 to follow A, T3 and T4 to follow C. So all four cases here lead to the same balance case, right? Lead to the same rebalance case. Now, this particular operation is called restructuring. So whenever we use the keyword restructuring, then we're going to come back to this particular operation, and then we're going to do it. Now, what is the intuition behind this? Well, the intuition behind this is that if you look at the structure of the tree itself, so it looks lopsided, right? Because what we say here is that this is, so 1, 2, right? So that means that all these trees, they are below, the T2 and T3 are below T1, and they're below by 2 steps. And so how do we make them more balanced? Is that we're going to make them more balanced by taking the grandparent Z and pushing it down. So when you push Z down, effectively, then you're going to add to the height of the T1 and T2. So in this case, or the left subchild, right? If this is H, then with the addition of Z, now this is H plus 1. Now, if this is H, then this is again H plus 1. Now they are balanced. Previously, if this is H, then this is H, this is H, then this is H plus 1, this is H plus 2. So it's lopsided. So when you restructure them, you push the Z down so that the Z is going to contribute to the height of the left one, right? Or in this case, a shorter one. And then the taller child is going to get pushed up and is going to reduce the height by 1. So bringing back the balance between the two sides. Now, so this is essentially the basic operation to rebalance the tree. And we're going to take a look at a couple of different structures. One is called an AVL tree. and the other one is called red-black tree. But on the way to red-black tree, we need to talk about 2, 4 trees. Now, how they are different is that in the case of the AVL tree, we are going to do regular rebalancing after every time we insert or remove. So every time we do something, we may create an imbalance, and therefore we are going to correct for the problem by running a rebalancing, a restructuring. Now, the other way to do it is by constraining the growth of the tree. So that means you have a tree that you're going to grow, but you're going to grow it carefully, making sure that every step of the way, you're going to keep it balanced. And in that case, these are for the other 2 cases of the. Okay.